In this video, we're going to start looking at how magnetic fields are created. Magnetic fields are created by moving charges, and the easiest way to do that is to set up a wire with current going down it. So in order to model the current in a wire, we're using the cylinder object in GlowScript. In order to define a cylinder, you need to give it a position vector. Now this position is a little bit different than when you work with a sphere or a box, because this defines the end point of the cylinder, not the center of the cylinder. And the reason for that will become evident when we get into the physics of it. You also give it a radius for visual sake, and you give it an axis vector that determines where it points, or the direction in which it points. So this is where one endpoint is located. This is the direction that the cylinder points. We're making this cylinder for the wire semi-transparent, so we're giving it an opacity of 50% so that we can place inside of it an arrow to tell us what direction the current is going. And the magnitude of the current we're adding on with this current argument. This is normally not added on to a cylinder, but we can add on whatever attributes we want, and Python just assigns those to the cylinder object. And just like before, we're adding that to a list called sources. So sources is where the field is coming from. So instead of being a collection of charges, now our list of sources is a list of currents. And like I said, we want to be able to envision what direction these currents are going. So I've also set up a list of current arrows. Not the previous arrows, but the current arrows. Haha. And so basically for each cylinder in our sources list, we're adding on an arrow that's embedded in the center of the cylinder. So we're doing the source.pos plus half of its axis to give us the location. And then the direction for this arrow, the axis for the arrow, is given by the source's axis times this current scale. And so the direction of the source and the size of its current determines what direction and how long the arrow points. This is going to be white, so we'll have a white arrow embedded inside a green cylinder. And then we have to create our observation points. This is set up pretty much the same way we've set up observation points before. Here, I want to be able to add in different sources, so I'm calculating the center of the sources. I'm also calculating something called the width of the sources to give you an idea of how wide the current, the set of wires is. And so here we're taking the maximum of the current source's width and the length of the source that we're looking at, just so that we can make sure that our observation points are outside of whatever mess of current we've got going on inside. And then here we create a circle of observation points centered around that central point. So every location starts out at the center of the set of sources, and we just add on to that this little circle position vector here, our cosine theta and our sine theta. Currently, our radius for that circle is going to be 50% greater than the width of the current distribution. That's just so that we make sure we've got a nice clearance around it. We'll be adding more later on, don't worry. Next we have a time loop. I'm going to ask you to ignore that for now until the next video, because I want to show you something cool with it that we'll do later. Same thing with this, with these comments here. Please just ignore that for now. We will get to that, I think, in the next video for time's sake. And then down here we have the actual calculation of the magnetic field. So we have a lot of geometry set up, and then these few lines are the actual physics going on. And so for every source in the set of observation, for every point in the set of observation points, we loop over the sources and add together the magnetic field for each of those. And so what we're doing is looking for the magnetic field point, so that's what we're calling point here. That's going to be an arrow that points. The magnitude of it is given by the mu naught over 4 pi. So this is the equivalent of 1 over 4 pi epsilon naught. It's the magnetic constant instead of the electric constant. We take the source's current value, so the higher the current, the higher the magnetic field. And then we take a cross product. So magnetic fields love cross products because magnetic fields come from a cross product, and the magnetic force has a cross product. So if you do a substitution of this equation into the force equation we had last time, you get a cross product of a cross product. So when you're dealing with magnetic fields, you have cross products all over the place. And what we do here is we take the cross product of the length vector of the wire. So this is why this axis vector is so important in the cylinder, why it's so important that the cylinder's position be defined as the endpoint, is so that we can have this axis vector to go right here into the magnetic field calculation. We cross that with the r hat vector here. So r here is the relative position vector. It's the why do I have a minus there? Oh yeah, sorry, yeah. So it's the observation point minus the source point. That's right. Yeah, I was looking at the wrong part. So this is the point we're looking at, and this is the point we are. This is the location of the current that we're getting the field from. So this is where the math gets a little bit messy because we have to get the center of the cylinder, not the end point. So this gives me the end point, and this gets me to the midway point. So we take that vector, we're dividing by its magnitude squared. So the magnetic field goes like 1 over r squared, just like the electric field goes like 1 over r squared. And we have its unit vector, r hat, over here. And then for visual sake, we have our magnetic field scale factor here at the end. So now that we have an idea of how this is set up, let's hit Control 2 to see what we get. So here in the center, we've got our cylinder of current. So it is a green wire. And we've got our current going through in this direction. So the current is going into the screen here. And then we get our magnetic field vector in blue going around the current. So because we have that cross product here, we end up with our magnetic field going around in a circle. The cross product makes things go in circles, basically. So the way to visualize this is with another right-hand rule. Physics 2 is full of right-hand rules. You take your thumb and point it in the direction of the current. So in this case, that would be pointing left. And then using your right hand, to specify, take the thumb of your right hand, point it in the direction of the current, and then your fingers of your right hand, your other fingers, the thumb in this definition is not a finger, it's a thumb, will curl in the direction of the magnetic field. So your thumb is going in the direction of the straight going thing, your fingers are going in the direction of the curly thing. We can verify that if we flip the direction of the current. So let's go back to our code here. Let me go up to the top. So I'm going to comment out this source, this current, and I'm going to introduce a different wire that's got all the same properties. It's got a slightly different position. It's over on the other side of the origin, but it's got the same value of current, but it's got its axis pointing in the opposite direction. So if I hit Control 2. What I get is a current now coming to the right. So if you use your right hand rule, you point your right thumb in the direction of the current, and now your fingers curl the opposite way. They're curling toward you as you go, as you come around the top of the wire. So this is a neat way to visualize the right hand rule. Of course, I could also have multiple current sources. Let's uncomment this one. So now I've got one going into the page, and I've got one going out of the page. And you see that these these magnetic field vectors kind of cancel out when we get up here because we've got some magnetic field going this way, some magnetic field going this way. Of course, on the ends over here, you're more close to this wire, so you get a greater magnetic field going this way. Over here, you're more close to this wire, so you get a greater magnetic field going this way. You get a pattern like this. In the next video, I want to set up an entire loop of current because it's kind of artificial to have current just going in a single wire. But before we do that, I want to take a look at one more thing here. I want to create more magnetic field points. So let's add more points to our list of sources. Let's get one set that's even closer to the wires, and let's get one that's even farther from the wires. So we'll go to 50% of the radius, 20% of the radius, and 80% of the radius away. And here you can see how that 1 over r squared effect comes in. That as you get farther away, the magnetic field gets weaker. In fact, I can add one more into that, can't I? Let's get even closer. Let's copy and paste. Let's get to 50% there. Oh no, that is way too much. Too close, a little too close. Let's go to 70. Actually, let's just go to 1. Let's go to 100%. There we go. Should have picked out that value beforehand. Cool, so here you can see how the magnetic field get stronger as you get closer. In fact, this is an experiment you can do in your class. You can get some iron filings to go around this direction. You can see that it ends up being stronger as you get closer to the wire. So next time we'll take a look at setting this thing up in a loop, and we'll take a look at what happens when we change the current with respect to time. So thank you so much for watching. I will see you next time. Bye-bye.